This is Algebra 2, Lesson 7-6, Natural Logarithms. In 7-2, we learned that the number e was approximately equal to 2.71828 and can be used as a base for the exponents. The function y equals e to the x has an inverse, and that inverse is called the natural logarithmic function. So in the natural logarithmic function, if y equals e to the x, as we see in this first graph right here, right? I'm going to highlight it. It's highlighted in yellow. This is the y equals e to the x graph. Okay? Its inverse is the natural logarithm, which is y equals the natural log of x, which is this one right here. Okay? Now, the same properties that apply to common logs also apply to natural logs as well. In the same way that you use a common log, you can use a natural log. So, if we have y equals e to the x, then x equals log e to the y, which is the natural log of y. So the natural logarithmic function is the inverse of y equals e to the x. So you can write it as y equals the natural log of x. So if y equals e to the fifth, then the natural log of y has to equal 5. And if the natural log of b equals 6, then b equals e to the 6th power. That's basically what we're saying here. Same rules apply to natural logs as common logs. So we can simplify them the same way we simplified common logs. So if I have 3 natural log 6 minus natural log 8, and I want to write that as a single logarithm, the thing you need to understand is it's really hard for me to write a natural log looking like an L rather than a 1, so I always put my L's as cursive. So when I write them, they're going to be in cursive. When I type them, they're going to be obviously typed. So basically, I have 3 natural log of 6 minus the natural log of 8, which is saying the natural log of 6 to the 3rd power divided by 8, because we use the properties of exponents here, which would be the natural log of 6 to the 3rd power is 216 over 8, which happens to be the natural log of 27. Oops, equals 27, the natural log of 27. So there's that written as a single logarithm, as a natural log versus a common log. The only thing is, instead of putting log, you put ln as the natural log. Okay? Now, we're going to write each expression as a single logarithm. So now we're just going to be using natural logs instead of common logs. So this is subtraction, which means division. So I have a natural log of 12 squared over 9, which is a natural log of 144 ninths. Okay? Which happens to be 16. Natural log of 16. There it is as a single log. 3 natural log x plus natural log y becomes the natural log of x to the 3rd times y, because we're adding, we know that's multiplication. So to clean that up, it's the natural log of x to the 3rd. The same rules apply, same properties of logarithms apply to natural logs as do common logs. So if I have 1/4 natural log 3 plus 1/4 natural log of x, that becomes the natural log of 3 to the 1/4 times x to the 1/4. Okay, because they're added, it means multiplication. Okay. So that could be written as the natural log of 3x all to the 1/4 power if I wanted to, which is the natural log of the 4th root of 3x. Which they actually use it this way. They put it in radical form versus exponential form. 3 natural log x minus 2 natural log of 2 is going to be the natural log of x to the 3rd minus the natural log of 2 squared. Since it's subtraction, it means division, so it's the natural log of x to the 3rd over 2 squared, which is the natural log of x to the 3rd over 4. It's not very hard. Just remember you apply your rules the same way you apply the rules with the common logs. Okay. Now, you can use the inverse relationship between the functions y equals the natural log of x and y equals e to the x to solve certain logarithmic and exponential equations. Remember before, when you took a log that was base 10, so we took 10 to the whatever power. Now, if it's a natural log, it's going to be base e. So if I have the natural log of 3x plus 5 squared equals 4, okay, basically that's the same. Right? If I took it, remember before when this was log, it would be 3x plus 5 squared equals 10 to the 4th. But see, since y equals e to the x, okay, so, and y equals the natural log of x, basically what I have is I have 3x plus 5 quantity squared equals e to the 4th power. So instead of saying 10 to the 4th, when we use the common log, we use 10, it's base 10. When you use a natural log, it's base e. So you're going to do the same properties as you did before, but now instead of using a 10, it's e. So I have 3x plus 5 squared equals e to the 4th. So if I took the square root of both sides, I have 3x plus 5 equals plus or minus e squared. Okay. So if I wanted to solve this, I would have 3x equals, I can do negative 5 plus or minus e squared. And then divide all that by 3. I would have x equals negative 5 plus or minus e squared over 3. And then if I wanted the approximate answer for that, I would put in my calculator negative 5 plus e squared divided by 3, and negative 5 minus e squared divided by 3. And if I do that, I'm going to get x would equal approximately 0.79635. Okay. And x will approximately equal to negative 4.12, negative 4.12968. So there you have, finally, this would be the exact answer right here, and these would be the approximate answers down here. And depending on what they're asking you for, maybe they're asking you for both. I know I would like to see the exact answer before you give me the approximation, so I know how you got to the approximation. So you might as well get used to writing both anyway. All right, let's take a look at some more of these. Solve the natural log of x plus 2 over 3 equals 12. So if I wrote it in exponential form, I'd have x plus 2 over 3 equals e to the 12th power. Okay. So if I was to cross multiply as a proportion, I would have 3 e to the 12th power equals x plus 2. So 3 e to the 12th minus 2 equals x. And if I put that in my calculator, 3 times e to the 12th minus 2 is going to be x equals approximately equal to 2. All right, here it's 3. And by the way, your e key is above your natural log key, like your 84. It's, you know where it is in the Inspire. So the 12 power minus 2 is going to get me, okay, 48,800. 488,262, 488,262.37. A very large number because e to the 12th will be very large. All right, natural log of 2x minus 4 to the 3rd power equals 6 means 2x minus 4 cubed equals e to the 6th power. All right, so take the cube root of both sides. You're going to get 2x minus 4 is going to equal e to the 2nd power. All right, because 6 divided by 3 is 2. And then you get the cube roots of these. So you get 2x minus 4 equals e squared. All right, so 2x is going to equal 4 plus e squared. So x is going to equal 4 plus e squared all over 2. Stick that in your calculator, you're going to get x is approximately equal to 5.69. Okay, so exact answer, approximate. Okay. So let's do one more. The natural log of 2x plus the natural log of 3 equals 2. Well, first I've got to get this into a single logarithm. So this would be the natural log of 2x times 3 equals 2. Because remember, when we add them, we're actually multiplying. So it's the natural log of 6x equals 2. So 6x is going to equal e squared. So x is going to equal e squared over 6, which means x is going to be approximately equal to 1.2. Now, you can use natural logarithms to solve exponential equations as well. And we were solving natural logarithm equations before. Now we have an exponential equation. So I have 7e to the 2x plus 2.5 equals 20. So the first thing I'm going to do here, 7e to the 2x plus 2.5 equals 20. I'm going to subtract that 2.5. So I now have 7e to the 2x equals 17.5. So, I'm going to divide both sides by 7 now. So I now have e to the 2x equals 17.5 divided by 7 is 2.5. Okay. So now, to get this to solve, I'm going to take the natural log of both sides. So if I take the natural log of e to the 2x equals the natural log of 2.5. Okay. So I'm going to move this over here so I can actually see it. So this becomes 2x natural log of e is going to equal natural log of 2.5. Well, by the properties of exponents, I just will simplify. Okay, now the natural log of e to the e cancels itself out. It's like saying log 10 of 10 equals 1. The natural log of e is equal to 1, so we basically now have 2x equals the natural log of 2.5. So x will equal the natural log of 2.5 over 2. And that is approximately equal to 0.45814. Exact answer and the approximate answer. Okay. So let's look at some more. All right, for e to the 3x plus 1.2 equals 14. We're going to do the same basic property here, same things. I'm going to subtract 1.2 first. So I'm going to have 4e to the 3x is going to equal 12.8. Okay, so now I'm going to divide by 4. So e to the 3x is going to equal 3.2. If I take the natural log of e to the 3x equals a natural log of 3.2, so I'm going to have 3x natural log of e equals natural log of 3.2. Okay. So basically these cancel themselves out, so 3x equals natural log of 3.2. Divide by 3. X will equal, oops, my approximation, add that to equal to. X will equal the natural log of 3.2 over 3. And then the approximation of that is x is approximately equal to 0.3877. And how many decimal places you take it to depends upon what you're told in your instructions. The book will either tell you or I will tell you how far I want you to go if they ask for a decimal approximation. Equal to, accurate to 4 decimal places, rounded to 3 decimal places, whatever. All right, here we go. B, e to the 2x divided by 5 plus 7.2 equals 9.1. So again, subtract 7.2. Do the subtraction part first. So we have e to the 2x over 5 equals 1.9. Okay, so the natural log of e to the 2x over 5 equals the natural log of 9. Okay, so basically we have 2x over 5 natural log of e equals natural log of 1.9. These cancel each other out, so 2x over 5 equals the natural log of 1.9. Okay. So basically, if I want to cross multiply to solve this equation, I have 2x equals 5 natural log of 1.9. x will equal 5 natural log of 1.9 all divided by 2 to get x by itself. And that's approximately equal to, so put on the calculator, 5 natural log of 1.9 divided by 2 is going to be 1.6046. All right, last but not least, last example, e to the x minus 2 equals 12. So that's already in simplified form. We don't need to add or subtract anything, so I have the natural log of e to the x minus 2 equals the natural log of 12. So x minus 2 natural log of e equals natural log of 12. Let's cancel, so x minus 2 equals the natural log of 12. So x will equal the natural log of 12 plus 2. And it does not become 14 because the natural log of 12 cannot be added to 2 because it's not a natural log. So you actually have to take the natural log of 12 and then add 2 to that to get your basic answer of x is approximately 4.48. I don't think that becomes a natural log of 14 because it's like saying 12x plus 2 does not become 14x. All right, the last thing we're going to talk about here is the real-world connection. Okay. A spacecraft can attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. The formula for a rocket's maximum velocity, v, in kilometers per second is v equals negative 0.0098 t plus c natural log of r. The booster rocket fires for t seconds and the velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket with fuel to its mass without fuel is r. So, suppose a rocket used to propel a spacecraft has a mass ratio of 25, an exhaust velocity of 2.8 kilometers per second, and a firing time of 100 seconds. Can the spacecraft attain a stable orbit 300 kilometers above the Earth? So, if r is 25, that's the mass ratio, okay, c is 2.8 because that's the exhaust velocity, and time is 100 seconds, we need to find v. So we're going to take this formula, okay, v equals negative 0.0098 t plus c natural log of r. We're going to plug everything in that we know. Okay, so v equals negative 0.0098 times 100, which is 100 seconds, plus c, which is 2.8, natural log of r, which is 25. So now that we have that, we just simply need to put it in our calculator. Okay, so if I put this in my calculator, negative 0.0098 times 100 plus 2.8 natural log of 25. I stick that in my calculator, I end up with the velocity is approximately equal to 8.0328. If we go back to our original problem, that's the maximum velocity of our rocket. The rocket can hit a maximum velocity of 8.0 kilometers per second, which, coincidentally enough, is greater than the 7.7 we need to, okay, it needs to reach a velocity of 7.7. It's greater than that, okay, because we just found the velocity for the maximum velocity. So since 8.0 kilometers per second is greater than 7.7 kilometers per second, the spacecraft can attain a stable orbit. There we have it. That's the application of natural logarithms. So we've talked a lot about logarithms in this chapter, which for some of you may be a really foreign material, and for a lot of your parents, they've never seen them, because unless they've been in upper level math class, logarithms aren't used as much as they used to be used due to the fact that we no longer have cycles.